Hello, this is a brief and concise visual tutorial on how to use the Cadence VLSI tools, and we're going to go through the whole flow while designing a simple cell, an inverter, but we're going to demonstrate all the steps, which are creating a library, creating a cell in the library, capturing the schematic of the cell, simulating the functionality of the cell, pre-layout, then doing the layout of the cell, checking for electrical rules compliance, checking for geometric rule compliance, DRC, and also extracting post-layout circuit from the layout with parasitics, and then doing the simulations or repeating the simulations with the extracted parasitics. So the first thing that we want to do, as indicated in documents that you were sent, we want to establish a secure shell connection with the virtual machine that CMC has set up for us. You can use any client that supports that connection, such as PuTTY. I use Hyperterminal, but I realize that that's not a free tool. But again, you can use PuTTY and use the IP address that you were given. So I'm going to bring up Hyperterminal, and I already have a connection saved with the parameters. So again, that's the IP address that you were given, and again, we're using a secure shell connection over TCP/IP, and I'm going to say OK. So it's going to connect, and you're going to log in with the ID that you were assigned. The first time that you log in with your ID and the temporary password, the system is going to force you to change your password, and then you should log out and come back in with your actual password that you will use from then on. So my ID is TCNJ-D01, and I'm going to put my password, and now I am connected to the virtual machine that we have been set up with. Now, once you're there, you want to start a session so you can connect with the nice desktop cloud visualizer. This is a DVC session, and you can also list the DCV sessions that you have. For example, I can say DCV list sessions, and I can see that I already have a session running. But as the document that you were given indicated, if you don't have any sessions that are running that you own, then you would use the DCV create session to set up your session. And if the system doesn't list the session, but it tells you that it cannot create it, what that means is that there is some other owner that is using a session with the same name. So you just have to make sure that you can create and then verify through the list sessions command, or the DCV list sessions command, that the session is there running and that you are the owner. So you could choose a name, any name you want. So maybe you want to use a name with your own name and some number concatenated with it, something that you think is going to be unique that nobody else is going to use. So I already have a session, so I don't have to create one. What I have to do is bring up the desktop visualizer, and that's going to get us into the Linux desktop. So I already have it pre-typed, but you would put that IP address that you were given /pound and then the session name that is running that you under your ownership, and then I'm going to say connect. Then it's going to come up with the username, so you log in again with the same ID and password. And then I have my Linux desktop. Once you are in your Linux desktop, you can go to the settings and change the display resolution. So in this case, I already have it set up for the maximum. And then you can go to applications under system tools and bring up an extern. So in my case, I already have an extern running in the session, and you should change to your project directory. So in this case, I'm already there in my project, and from there you want to run or source the initial script that is going to set up the environment for the Cadence tools. So in the xterm, if you have run a command line before, you can sequence through the history with the up and down key arrow keys. So I know that I already have sourced that script, so I'm going to do it again and look for the command line to source the initial script. So this is in your document that you were sent. So I'm going to do it again, and is going to tell you some information depending on the state of your environment. But what you really care about is the last line that it says virtuoso, which is how to invoke the tool. So again, I have used that command before, so I'm just going to look for it. Normally, the only thing that would change is the number of the log. So in this case, 3170, I already have that. So I'm going to just issue that command line. And now we're going to get the main console of the Cadence tools. So once you are there, the first thing that we want to do is to create a library. So we're going to say new library, and we are going to attach that library to an existing technology library. This is the library that is going to have all the components for our PDK, all the rules, and so on. And we're going to name, give a name to our library. So in this case, I'm going to call it mylib02, and I'm going to say OK. Then it's going to ask me which technology library I'm going to attach this library to. So ours is going to be the GPDK 045. So we select that, say OK, and now our library has been created. Then we're going to go back and now create a cell, the schematic view of the cell that we want to design, which is in our case a simple inverter. So we're going to say cell view, and it's going to be in my library 02, and the cell I'm going to call it my IMV01, and we're going to create a schematic view of that cell, and it's already populated with the right application to use for that. So all we have to do is put the name that we want and then say OK. And that's going to bring up the schematic capture application. So I'm going to maximize that, and I'm ready to start placing components or instances. So I'm going to go here to the Add Instance dialog, and I'm going to select the library GPDK045 that has my components. And I'm going to place an NMOS, so just the 2 volt NMOS, which is really a 1.8 volt VDD. So I'm going to select that component, and normally in a design you pre-calculate the initial values that you want for the electrical channel width of your transistor, and you can change it here. You can also select the number of fingers geometrically of the transistor, but in our case, for this simple demo, we're just going to choose the default. So we're going to leave that the way it came and place our NMOS over here. Then we're going to hit escape, go back to the instance placement, and now we're going to select a PMOS. So PMOS 2 volts, which is the corresponding one, again with the defaults, and we're going to place it somewhere here. And hit escape. And now we're ready to connect our transistors so we can add some ports. So with the mouse wheel I can zoom in and out. So this is a good level here. So I'm going to go to create narrow wire, and I'm going to connect the gates. I'm going to also make a net connection here to put a port for the input. Hit escape, go back to add wire. I'm going to connect here a net to put the VSS port, and another net here. And actually I'm going to expand this a little bit, because I'm going to need to make connections for the bodies of the transistors. So that's going to be here. So the body of the PMOS connects to the source, and the body of the NMOS connects to the source of the NMOS, and then I connect the drains together. And I'm going to have this net here to put the output port. So now that I have all the connections, I can add pins or ports. So here is the icon for that is going to bring up the dialog for the ports. So as you can see, it's not bringing up the dialog. Sometimes one minor bug that the DCV client has is that sometimes it gets stuck, and the easy way to unstuck it, and I've been told that this doesn't happen if you are in full screen mode, but since I'm not using full screen mode, it's happening. So the way to unstuck it is to change the resolution. So I can go back to 800 times 600, and you can see this, the dialog came up. So it wasn't showing it. And now if I go back to the resolution that I want, I'll have everything the way that it should. So I'm going to create a pin or port, and it's going to be an input. So that's going to be my A input for the inverter. Normally we use the first letters of the alphabet for the inputs and the last letters of the alphabet for the outputs, going backwards, starting with Y. And now I have my A, so it's showing here. So I'm just going to attach it to that point there. So here I have my A. Go back and recall the create pin dialog from the desktop over here. I'm going to add the output port called Y, and I'm going to change that to an output, and I'm going to assign assign it here to that net. Now I'm going to go back and connect VDD, so it recognizes the name, and it changed the signal type to power. Also, I want to make normally power ports input output, and I'm also going to rotate it right because the connection is vertical. So I'm going to do that, and I can see the connection point there. So that's going to be my VDD point. Going to go back and now assign a new port VSS, and again it's going to recognize that it's ground, and it's already vertical, but that's not the vertical direction that I want. So I want to do rotate the opposite direction left twice, and now I have that port the way I want it. So now I have all the connections, all the pins, so I can dismiss this dialog, and I can do a check and save. So that's going to do some preliminary checking for electrical rules of the schematic. So I'm going to do that. So nothing came up, so that means that it's okay and it is checked. Now that we have the schematic for our design, we want to create a symbol so that we can instantiate this inverter in another schematic, which is going to be the test bench. So we can actually test it and do simulations and make sure that our circuit works. So for that, we're going to go to create, and we're going to create a cell view from the cell view of the inverter that we have. So already knows that I want to make a symbol of it, and that symbol is going to have the same name. So all I have to do is to click OK. Then this symbol is going to be a box, and it's going to try to infer some positions of the pins that we can change. And also in the symbol editor, you could, for example, if you wanted the symbol to be like a triangle with a bubble to reflect what normally an inverter looks like symbolically, you could do that and edit it, but that really is a static issue. So we're not going to do that. We're going to take the box. The only thing that we're going to change is that we want VDD on the top, but we want VSS in the bottom. So I'm going to change that, and then we are going to click OK. And as you can see, it created a symbol that we can instantiate somewhere else. So now I can check and save that symbol. So that that is saved. So now I can use it. So now I'm going to create the test bench to test my inverter. So we're going to go back to the console, go to File, and we're going to create a new cell view, which is going to be a schematic. So it's going to be a schematic of the test bench. So I'm going to call it my IMV01 TB01. And I'm going to say OK. So that's going to bring up a new view or a new schematic capture editor window, which I'm going to maximize, and now I can start creating my test bench. So for that, I'm going to go to the instance placement. So I want to instantiate my inverter, and that inverter is not on the PDK library, of course. It is in the library that I assigned, that I started, which was mylib02, and the cell was my inverter. So you can see it there. So well, I'm just going to set it here. Hit escape to stop the replication. Go back to the instance, addition dialog, and now I'm going to add some components that I need for my simulation. I need to add power, I need ground connections, I'm going to add a small load, and I'm going to add a stimulus. So all that is going to be in the analog library. So first I'm going to add a capacitor as a load, and I'm going to add a 10 puff capacitor, small load, but I think these are minimal size transistors. They're pretty weak, so I think this small load is going to be able to show some distortion or some delay from input to output when we do the simulation, so you can appreciate that. So here we have our load over here, and we are going to escape the replication, go back to instance, and now we're going to add voltage sources. So we're going to go down to V source, which is the one that resembles most what we're used to from a SPICE. So this one here. So the first one is going to be power, so that's going to be a DC source, and we're going to make it 1.8 volts, and we're going to set it over here somewhere. And we're going to go back to the add instance, and now we're going to have a pulse which is going to have a delay of half a microsecond. The 0 value is going to be 0 volts. The 1 value is going to be 1.8 volts. The period is going to be 1 microsecond. The rise time, we're going to set it to 0.1 microsecond. The fall time also to 0.1 microseconds. And the pulse width we are going to set to 0.5 microseconds. So that should be everything that I need to specify for my input stimulus. So we're going to place it over here. And we can escape the replication. And again, if we were going to check the properties, the properties of this voltage sources, it would show it to us. Oops. So if we click here, it shows that this is a 1.8 volt DC. If we click on this one, it shows that it's a pulse. So you can see the actual properties of the different components. So now that I have everything there, I can connect all those components. But before that, I need to add some ground connections. So I'm going to add some ground connections. Here we have ground. So I need a ground for my input. I need a ground for my load. I need a ground for the actual inverter, and I need a ground for my power supply. So I can escape and go back to adding wires, and now I can connect those. I can connect, and again, you can zoom in and out with your mouse wheel. And then I have so now I have my test bench all wired up, and I can check it and save. So again, no issues came up. So now that I have my test bench, I'm ready to run the simulation. So to do that, I'm going to go to the launch menu and invoke the ADEL, which is the simulator, and that's going to bring up this this dialog. Then the first thing that we want to do is go to the analysis and choose what we want to do. We're just going to do a simple transient analysis with a duration of 5 microseconds, which is going to give us about 5 cycles of what's going on. Then we also want to select what outputs we want to look at out of the simulation. And we go to the output menu, setup, and then we're going to specify that we want to do that from the design. So we click on from design, then it shows us the test bench schematic, and we click on the nets that we want to look at. So obviously we want to look at the input, we want to look at the output net, we could also look at the ground and then the power supply, but that's just going to show 0 and 1.8 volts respectively. So we're just going to look at those two nets. So when we go back to the to this setting of the outputs, we can see that they have been populated in the table. So we say OK, and then when we go back here, we have them in the outputs as well. So at that point now we can run the simulation. So we go to the simulation menu and say netlist and run. And now our simulation comes up, and you can see the 5 cycles of the simulation. You can see that only 10 puff is enough to really cause some delays. You can see our specified input rise time about 50% of the cycle, and then you could actually zoom, and you can zoom in by 2. You can get a couple of the relevant edges, and then a scale on the y-axis here. So you can see there the input, the high to low transitions and the low to high on the output. So here we have a delay. You can see the actual numbers here. About 2.15 microseconds, and this is 2.24 microseconds. So we have about 90 nanoseconds of delay, and this is a little bit less. This is about 2.6, 2.58, so maybe 70 nanoseconds on the transition from high to low. And that should make sense to you. So this transition from low to high on the output is driven by the PMOS, and the transition from high to low with the NMOS. So we know that the NMOS is normally stronger, especially for this smaller default size transistors. We know that the NMOS is stronger, so it's going to be a bit faster on the high to low transition caused by the NMOS. So now we are happy with our simulation. We know, let's say that we know that our design works. So we can start closing everything that has to do with the simulation. So we can close the plot or the visualization tool, and this tool has a lot of more sophisticated measurement facilities. You can create expressions, but again, this is meant to be a very minimalistic type of overview. So we're going to close everything that has to do with the simulation. Just save that, say OK. Then we're going to close the test bench, and we are going to be well, we're going to also close the symbol editor, and we're going to be left with the only with the actual schematic of the cell that we designed and that we're happy with, and we're going to go on to the layout. To invoke the layout from the schematic of the cell that we are designing, we're going to go to Launch and invoke Layout Excel, and we're going to create a new layout automatically. So we say OK to that, and we are going to put it in. So the library that we're working with is already populated. The cell is already populated. It's going to be a layout view. So we say OK to that. And that's going to bring the layout window side by side with the schematic. Is a connectivity driven layout, so both windows are linked, and we can proceed to place our components automatically. So we're going to go to connectivity and generate all from source, and we are just going to, for this case, going to accept all the defaults. If you had a more complex cell, you will want to perhaps chain the transistors or fold them in the placement. So in this case we don't need to do that because we only have two transistors, and one is P and one is N. But the chaining and folding basically reuses drain and source regions on connected transistors that share those regions, so it gives you a more compact and optimal layout. So again, we're just going to take the defaults for now, so we just say OK, and you can see that the tool created a placement that is very conservative, very generous from the schematic. So here is our A port, our Y port, our VDD on top, VSS on the bottom. So it just puts some pieces of metal there. And here's the PMOS transistor and the NMOS. And again, they're just placed very conservative, so there are no geometric or DRC violations. And then by hitting Shift F, we can actually reveal the layers inside. So we can see with Shift F that what the transistors are. So this is the drains over here. We already have two contacts there populated for us. The gate of the transistors, and then the sources over here with contacts and all the other different layers. We can actually select which layers we see. I mean, this can be very busy. So we can go here and select the layers that we want. We don't want to see all the layers, we just want to see the used layers. So we click on that and we get a subset of the layers. Those are the layers that are in use that we're going to work with. So from here we could do a routing of the placement, but we really want to optimize this a little bit. So we're going to click on some empty space here. We're going to right click and then select or make the PR which is the cell boundary non-selectable. So we're going to do that. So when we select things inside, the whole thing doesn't get selected. The first thing that we want to do is we're going to move this N-channel transistor all the way to the bottom. So we're going to click on move and select it and move it all the way to the bottom. There. And we also want to get this PMOS closer to the N channel. So let me move this a little bit more. You can always zoom and basically make it so that's as close as I can get it to the boundary without going over it. So it was there, so I'm just going to hit escape. And now I'm going to move the P channel. And when you click on a component, it shows the connectivity of the different components and ports. So I'm going to move this, and I'm going to try to make it, let's say, right next to the N channel. Now what I'm going to want to do is to verify as I do things to make sure that I'm not introducing geometric or DRC rule violations. So I can do that here from the verify and hit OK. So it's showing me that, well, the main thing that I care about here is that I have the P implant here is too close to the N implant for about that much. So if I select move, I should be able to move it up, let's say to there, and then I can go to verify. I can go to markers, delete all, say OK, and then verify again. So that's still telling me that it's too close. So again, I'm going to move it up. Go back, delete all the markers. These are the error markers. And verify again. So you can see that the marker here for the distance between the P implant and the N implant are gone. So this distance from the P implant to the yellow N implant. So I'm going to leave the transistors placed in the vertical in that manner, and going to delete the markers for now. And you can see how much we saved. So now we basically, the top of our cell is going to be here rather than here. And we'll adjust the boundary later on. One thing that normally the routing, when we route the connections to the ports and between the transistors later, one thing that the router is not going to do is to connect the bodies. So we're going to have to do that by hand. And to do that, we're going to have to extend the endwell. So so we can just go to stretch and select, or actually we don't want, we cannot stretch that that well, because it is part of the transistor, so it's below, hierarchically is inside the transistor, so we cannot really edit it. It's a part. What we have to do is add or draw endwell. So here with the endwell layer selected, here we're going to create a shape, a rectangular shape, and we're going to sort of zoom here, and this also, let's go to the objects as well, and see if we can show the grids. Oh, it's right here, grids. So we want to show the grid, not the placement grids, or not the tracks either. But the placement grid, that's all we want. And it's going to show us this, if you really go, the grid is really fine, so you really have to go down to actually see it. But it's going to be there. So with that, we are going to draw a rectangle of the endwell. So create shape, rectangle, and we can overlap the layers because they're really the same material, so they can overlap. It's just the same thing, and that's a safe way of a safe way to make sure that you get a continuous piece of material and you don't get errors later. So here we're going to draw a piece of well, let's just say all the way there, okay? And we know that the well, the end well for the PMOS is the body, so it labels it as BDD because in the schematic we already connected that to BDD, but we don't have the physical connection yet. To have that physical connection, what we now have to draw on the well is since it's an end well, we need an end implant region, which is going to be to create shape rectangle. So we're going to create, and we know that this is P implant here. So the end implant has to be this distance that we see here from the from each other, and it just has to be enough to capture a contact. So we're going to draw that there, and that looks we can move it a little bit to be more aligned with the we can move it in the center here. So let's just leave it there and run a check, and if it's too close to the, if this N implant is too close to this P implant, then it will tell us. One thing that I can do is actually turn off the thick oxide so I can actually see, and actually I can also turn off the gate oxide so I can actually see just the implant regions, and so here we're going to do a verification, so see if we are too close. And we are it is showing that we are too close. Also the metal here is too close to the well. We'll fix all that later, but for now I'm going to remove the markers. And I'm going to move this a little bit to the left. And I'm going to run the verification again. So this is telling me that the region is too small. Actually, we may be okay with the distance. So actually what I'm going to do is to delete the markers. And I'm going to stretch, just make it twice as big. So this is uses stretch, and here is showing me that it's ready to be stretched. So I'm going to make it twice as big, and now I'm going to stretch this one this way. And I'm also going to move it down. And this is it's moving on the grid. And move it down a bit. Set it there, and now move it this way. Let's just set it there and run our DRC again. All right, so I don't see anything, any markers between this P implant and N implant, and also I don't see any markers on the side. So I'm happy with that connection. The only question is on the size of this edge of the P well, whether it is too far. Certainly it's too close to the metal, so I have to do something about that. But I may be able to move it back a little bit. So I'm going to delete markers again, and then stretch this edge of the endwell. Oops. Stretch this edge of the endwell about let's say there. And we're going to run the verification again. So I'm still getting okay, so this error that I'm getting here for the metal, it's just that it's too small. But that will go away when we route things. So I'm just going to leave that area there. I'm going to remove the markers. So one thing that I'm going to need on this N implant is a contact. So we're going to go to the contact and say create a rectangle, and I'm going to draw a contact about the size of this contacts over here. And I'm going to verify again. I don't really want to go too far, so this is telling me that that contact is too small. I'm going to stretch that a little bit. So let's see if he likes that. You could actually have the rules in front of you, the numerical rules, actually how many nanometers of spacing and in needs and width and so on, and count with the grid, count the spacing, but that may actually take more time. So that contact actually looks larger than the than this one's over here. So I'm not going to believe that for now. I'm going to do the same thing and create a contact to the body on the for the N channel. So that since this is an endwell process, that means that the bulk is P type. So normally, to be explicit, they introduce a layer that is called a dummy P well. I mean, a dummy P well. You can see it here. So we can actually replicate that dummy P well. So we're going to have a region that overlaps with that. So we're going to draw a rectangle of dummy P well. So we're going to create shape rectangle, and we're going to make it from here to about the same as the end well. So we want a width. So that width is, if we read down there, the width is 0.565. So we're going to have it coincide there and be Um, and again, that is going to mark it as VSS because we had the body of the body of the um, N channel connected to VSS. And then what we need here is a P implant and a contact to make that connection. So we are going to select P implant as a drawing layer, and we're going to create a rectangle. So if we want to get a rectangle the same size as this N implant, we can come over here and just draw it on top and then move it. And so we can move that in implant, or P implant rather, to sort of in the center here. And we can also then put a contact. We have to put a contact in there. So we are going to do a copy of that contact and put a contact there. So let's see where we are. Can go to view, zoom to fit all. So at this point we want to save what we have, and we want to escape out of the mode that we were, and right click on the outside of the cell and select make the PR boundary selectable. So now we can go and stretch the boundaries. So we're going to have our top boundary there, and we're going to bring in this boundary here. So you can see that we have made the cell much smaller now. And there. So now we're going to zoom to fit all. So now we're going to optimize the placement of these ports. To do that, we're going to go to VSR view and we're going to expand the pins and we're showing that we have problems with three of the pins because they're really outside the boundary of the cell. So that's really what the problem is. So we can go to each one of them and go to place, go to pin placement, and fix that. So we can select it here. Let's just move this over here. So you can see that it's selected, and we can say apply and place, and it moves it. Then we can do, we actually did that for all of them. So now all the pins are inside the boundary, and they show here they're okay. So I can close this. All right, so now I have a layout that is pretty well optimized for size. So I can come back here and zoom to fit everything. That gives me a better view. Now I have to route the nets, and here I have nets that are not routed. So I'm going to go to route and do automatic routing of all nets. So normally you can see that it routed the signals, although I'm actually going to undo that because well, we're gonna leave it for now, but one thing that you could have done is to basically stretch the poly, so basically you're connecting both gates with poly, and that's okay. This is a very short distance, and then just have a single metal connection to the poly with a contact to poly here. But we're just gonna leave it like that. But the power, it wants you to create a power rail, and we're not going to do that. So we're going to go explicitly and say VDD, go back to route, and say selected nets. So now it made a connection here, but also we're going to connect here by drawing metal, because still showing that there is an open connection. So we're going to create, well, let's just do the VSS, the other part, by doing route selected net. So that's going to connect VSS here, and let's just connect here and here manually. Before that, we're going to save. So we're going to go back to the classic view, and we're going to select metal one drawing, and we're going to create a rectangular shape which is going to extend and there. So now let's zoom. So now one last thing that we want to do is to also uh, add some more thick oxide over the area of the connection that we have made here. So we're going to pick that layer as a drawing layer and go to create rectangle, and we're going to extend the oxide all the way down here. Like so, and also over here. That looks the same, and let's so we have basically taken care of those connections. The other layer that we're not showing is the thin oxide, which is really just for the gate. Let us say what we have. So at this point, one thing that is not the best practice that I did here is to use metal in these two contacts over here. So I'm going to go over here and actually delete. I'm going to delete this piece of metal, and I'm also going to delete this contact over here. Oops, that's not what I wanted to do. So I want to delete those contacts. Sometimes you have to really get really close and zoom in there, and then I'm going to see then I'm going to see if I can stretch this poly here. So now I have the two gates tied in poly, and I'm going to go back to for some reason deleted the I'm going to go back to the routing over here, and so that looks good. Now we're going to go back. Go back to classic and look at my wells are. So it actually deleted the wells that we had drawn. So we're going to place those again, or draw those again. So I must have done that by mistake. So create shape, rectangle of endwell. Like so, and then create a rectangle of dummy p-well. Let's look at them. This is gate oxide, field oxide, like that. Poly, P implant, N implant, contacts, and metal one. Okay. We still have to recreate these connections here. Let's go back to selecting contact as the drawing layer and creating Getting wiring from here. And then selecting contact. Selecting contact, shape, and we can move that. And then stretch the metal over here. And we can do the same thing on the bottom end. Oops. Now we want to create rectangle. Many of our actions are bound to keys that you have to remember, but I really don't remember. And now we're going to move that contact a little bit. And then stretch the metal. Oops. That's actually good there. All right, so we're going to zoom to fit all, and we have our layout completed, and we're going to save it. So now we're going to run DRC with PBS, which is more comprehensive tool. It can tell us actually what's wrong, and we can make a real judgment on whether it's a real error or not. So we're going to run DRC. And we're going to call the directory DRC run. Then we're going to go to the rules and load our rules and select the technology. So now once we have selected our technology, then we're just going to say submit. So this got stuck again, so we're going to change the resolution and come back. So I found no errors and 4 warnings. Okay, so that's good. Now keep in mind that you may finish a cell without tying the body. Again, if you have cells that or transistors that share a common body, you can have normally one connection per 10 transistors. This is a good rule of thumb. You don't have to have one body connection per transistor, and the reason is that it's very expensive, as you can see, because you have to use, in the case of this PMOS, we have to use an implant to tie the endwell, and the implant regions of different polarities have to be quite far apart by design to be able to fabricate it. So that adds all this space here that is very expensive. Same with the NMOS. So here we have only 4 warnings, which really don't really mean anything, but we have no errors, so that's great. So we have a geometrically clean layout. So we're going to close that. The next check that we want to make is layout versus a schematic check. And for that, we're going to go to the PBS and run LBS. So we're going to get the dialog, and we're going to designate that run directory as LVS run. Then we're going to go to the rules files, and pick the our rules. And then in the input tab, we're going to change convert pin to geometry plus text. and we're going to select, no, this is okay. Here in create CDL, we're going to select auto CDL, and on the output tab we're going to check create Quantus input data. This is going to be used later for the parasitic extraction or the simulation of the parasitic extraction. Then we're going to select apply, and it's going to run. All right, so this is good news. We have ERC results are empty, which means there are no errors. The extraction is clean, and the comparison of layout versus schematic matches. So at this point we say no because we don't want to run LVSDE. We're happy with these results, so we say no, and we can close this dialog. So once we have run DRC and the LVS, we are ready to do the parasitic extraction with Quantus, and we're going to run PBS Quantus, and everything should be populated for us. And the only thing that we want to check in here is that we select transistor DSPF and that the file name is our cell name.dspf. We also want to make sure that we check the add LVS MOS diffusion resistors, which is really in plant. We want a level of 3, and we want to uncheck accuracy downgrade. We don't want that checked. Then everything else on that tab is okay. We can go to the, we have to make sure that technology is our GPDK 045 underscore PBS, that the rule set is RCX worst underscore worst, and then in the extraction we want the type of extraction RC, and we want the coupling mode for the cap coupling mode to be coupled, and for that we need to provide a reference node, which in our case is VSS. And in the extraction tab, that's all you need to change. The other tabs, nothing needs to be done there. Alright, so once we have set up everything, we can just hit run, and Quantus is going to run. So it told us that it finished successfully. So now we have our extracted netlist. Now that we have our extracted netlist, we want to do our bus layout simulation. And to do the bus layout simulation, we want to go to the library manager. So we want to go back to our console here, to tools, bring up library manager, and you want to select your library from here. So I have that selected already, and you want to select your test bench. So remember that it was my IMV01 TB01. Okay, so once you select your test bench, you're going to select new cell view. So here you're going to select your library, and you're going to select your test bench and a view which you're going to call config and of type config. And then open with hierarchy editor and you say OK. So once that comes up, you select the view, which should be a schematic, and then from the library list you're going to select your library, which is mylib02 in my case, and you're going to add it to the list and say OK. Then for the view list, you're going to essentially add everything. So you add everything by clicking on the first one and then scrolling down and shift clicking, left clicking on the last one. And every time I say click, I mean left click. If we have to right click, I would say that explicitly. So that we're going to include that and say OK. And then for the stop list, the only one that we want to include there is a spectra. So we're going to add that. And that's it. We don't need anything else. So we are ready to create that configuration, and we get this this screen. So here now you're going to look for your cell, which is my inverter 01, and you're going to click on that row and then right click and set cell view to specify a SPICE source file. Then you're going to look for that SPDF file. So it's right here, my IMV01 DSPF, and you open that and say OK. And now that is the file that is going to be used, the post layout extracted file instead of the pre-layout schematic. So once you do that, you can save the configuration, and now it's highlighted in blue saying that it found it with no problems. And now you can bring up the simulator again. So that's the ADEL. So you're going to open that. And again, you're going to do the same thing as before. You're going to choose an analysis. So in this case, we're going to run it for 5 microseconds. It should be enough cycles to look at things. And we're going to say OK. And then we're going to select our outputs. And we're going to say from design as before. And that's going to bring the test bench. So we're going to pick the input and the output node. So when we come here, it's on the table, so we say OK. Then we can go back to the ADEL, either from the desktop or we have it over here. We can see a piece of it. So we can see that the input and the outputs are there. And then we can start the simulation with netlist and run. So the simulation is going to start running, and this time is going to be using the post layout extraction. So you can see that the log and the screen, they look a little different as it runs. And here we have our results. So not real difference, if you recall, because this is a very small cell. So we wouldn't expect a lot of degradation or a lot of meaningful parasitics. But parasitics are a big deal in bigger cells. So now that we have finished our post layout simulation and we make sure that everything still works, we are done. We are just finished, and we can start closing everything. So we're going to close this plot. We're going to close this output window. We're going to close the simulator. We're gonna close, we're gonna say that state, so sure, yes, say OK. We're going to close the test bench. We can close the configuration manager and the library manager, and we can close our layout. So it got stuck, so I'm going to change the resolution. So I closed the layout, so it's gone now. I'm going to close the schematic, and I can close the main console, and that shuts down the well, first I have to shut down this library manager work area, and now I close the console. What does it need? I'm just gonna close the console. It should go away then. So everything is shutting down, and I'm back to my desktop with just the extern, and my flow is done. I don't think that a Spice netlist is something that you have worked or seen before, because it's always sort of hidden behind a schematic capture tool. But one last thing that I wanted to show was the extracted netlist. So to do that, I'm going to open the file manager and go to my project directory, and I'm going to look for that netlist. Is myinv01 DSPF. So I'm going to open that with the text editor and show you the Spice netlist that resulted from the extraction. As you know, the netlist that would result from the schematic would only have the two transistors. Those were all the devices that we had there. But as you can see, this netlist has a lot of capacitors. So you can see the capacitors instantiated here. SPICE is really a textual connectivity language in which you specify with text the connectivity of devices, and you can see that we have about 24 capacitors that are parasitic. We have, well, actually we have more. We have 28 capacitors and 10 resistors that are parasitic, and of course their values are they're really small. And it tells you in the comments which net the parasitics are coming from. Again, the values are really small, so this is less than the parasitics or the capacitances are less than femtofarads, and the resistances are a bit higher. I mean, as you can imagine, the metal lines are really thin. You can see resistances in the 45 ohms, 37 ohms, and for example, this will tell you that this is a resistor from a segment of VSS to another segment of VSS, and this is a resistance from the transistor zero source to a segment of VSS. So that's a piece of metal that we have there, and this would be um, a capacitance from the Y node to VSS, and this would be a capacitance from the input A to VDD. So this is just happening through the oxide layers and so forth and so on. So this would be all simulated in the post layout simulations. Also, for the actual two transistors here, MM0 and MM1, we can back annotate actual physical characteristics of the transistors. For example, the area drain, um, the perimeter of the drain, the area of the source, the perimeter of the source, and so on. So these are actual characteristics, physical characteristics of the transistors that come from the layout, which the model, the SPICE model of the transistors, uses to modify the electrical characteristics during simulation. So we're going to close that and close that. So this is a very brief, somewhat superficial flow, but it does go through every part of the flow. Again, the library creation, the schematic capture, the simulation, the layout, the DRC checking, the LVS checking, layout versus schematic, the parasitic extraction, and the post layout simulation. We did go through all the steps. And once I close everything, I can shut down my nice DCV client. I can shut down my terminal, and we're done. Thank you very much.